All right. Hi, everyone, and welcome back. So this is our first seminar of the semester. I'm very excited to have Natalie Collina today as our speaker. Natalie is a PhD student in computer science at the University of Pennsylvania. She works with like Michael Kearns and Aaron Roth. She does a lot of work at the intersection of algorithmic game theory and online learning, and she's really interested in understanding repeated strategic interactions and the algorithms that agents are going to employ in those kind of settings. She's supported by an IBM PhD fellowship, and she was before supported by Amazon WS at AI, and she's also the organizer of the theory seminar at Penn. And today she's going to tell us about her work on tractable agreement protocols. And Natalie, it's all you now.
Amazing. Can you all hear me okay?
Yep.
Yes.
Cool. Yeah, feel free to ask questions at any point. Just unmute yourself and go ahead and ask. I think this is especially like when we talk about sort of the core definitions here, I would much rather us, take a while, make sure we all understand them, then move on with people being confused. So very, very open to pausing and being flexible with like what we get through so we make sure everyone understands. Okay, great. So yeah, I'm happy today to talk about this work with joint work with Serbi, Varun, and Aaron, all also at Penn, called Tractable Agreement Protocols, which was actually accepted as stock 2025. Okay, there we go. Okay. Sorry, I just want to move. I don't know if y'all can see this, but I have this annoying little bar. Okay, that's fine.
We
Okay,
can't see it. I'm
wait.
assuming that's your like Zoom.
Okay, yeah,
But if it'll bug you, then you should fix it.
I've just done something strange where I've now lost.
Yeah, you've now ruined it, whatever you did.
Yeah, that seems about right. Let's see. Okay, here we go. Okay, just building the suspense. Okay, now can you all see it again?
Yeah, it looks good.
Yep.
Amazing. Okay, so the motivation for this talk is that humans, when making decisions these days, increasingly are using algorithms, using really complex algorithms, using AI to help them make decisions. And we want these interactions to lead to positive outcomes. So we have a motivating example where here we have a lovely doctor, and here we have a AI, a machine learning model, perhaps has a complex neural net that it's trained on, which is designed to help the doctor with medical decisions. So you can imagine a patient coming in for a little kid with a broken leg, and they have some features which might be immediately digestible by both the AI, the model as we'll call them, and the human. And, things that, can be like easily like seen on a chart, right? Like their blood type, like their past diagnoses. But there also might be a lot of other information that this model has access to just based on memorizing a huge amount of medical information about many, many different people, which has then sort of been compressed into these neural network weights, which aren't really, understandable at all by the doctor and might include information that's helpful for them for making a decision. Meanwhile, this doctor might also have some insight that isn't easy for the model to provide. Like they're actually seeing the patient that day, right? They can see their appearance, how they're acting. They can actually talk to them to pick up more information. And some of these pieces of information or expertise might not be something that's captured in the model. Okay, so what we want is for all of this information to be used to make a good decision about what to do with this patient. So say that the decision is, okay, should we operate on this patient? And the model takes all the information it has access to and says, okay, I think the risk of an operation is 20%. There's a 20% chance something goes really poorly. And see here, I'm very proud of this little animation. The doctor is frowning now because she doesn't agree. Now we think about that as a bad outcome, right? Okay. But it's also a little hard to think about, how can we possibly protect against this? This idea of agreement, it seems so, like not precise. But in fact, there is a precise notion of agreement that exists and that we can work with to try to get past this. So let's talk for a moment about something called Oman's agreement theorem. So Oman, great research dude in 1976. He did some work looking at what happens if you have two different agents who have a common and correct prior over state of nature. And then they also have sort of knowledge about how the other person's private information is generated, but not necessarily, they don't necessarily know their private information. And then, right, so there's their common knowledge, and right, but maybe they have like different actual hidden knowledge, right? Like I know that like you've had this surgery before, and you know that I was a top student in med school. So like you might have a prior on what I know, but you don't actually know exactly what I know. And now we sort of update our posterior distribution on your prior, and then we sort of continue back and forth. And the upshot is that you actually can't agree to disagree. That eventually, if you have this common knowledge, which is if you like continually back and forth are like, okay, I know that you know this, I know that you know that I know that you know this, we'll eventually agree. Okay, how does this relate to what we're doing? Because what we're doing is not actually common knowledge, right? Instead, we're thinking about exchanging information. But it turns out that this is also true in a finite sense, and that there's work related. So here you should actually really think about, I should have changed these bubbles to now being conversation, like, you know, like a conversation thing without the little dots, right? So now they're saying, okay, like this is what I think the risk is. Now this is what I think the risk is. And they will eventually actually converge to agreement in a finite amount of time. And this is assuming that they're both actual Bayesians, right? So when I see the information that you've given me, I'm gonna completely do a correct update on my posterior based on that. Does that make sense so far? Any questions? Okay, so most relevantly to us in this work of agreements, Scott Aronson in 2005 had a nice paper that showed, okay, so sure. So this protocol works in finite time, but that doesn't necessarily give a, you know, a strong upper bound on the amount of time it can take. How long can it actually take? And he showed that if you want to reach epsilon delta agreement, you can do so in 1 over epsilon squared delta many rounds. Now, what are epsilon and delta? The delta is talking about sort of the probability of success. It's saying, okay, well, we're going to take this randomness over the draw of the true state from the prior, right? And we want to succeed with probably 1 minus delta. And what success looks like is that the expectations of the agents and messages differ by at most epsilon. They don't have to be exactly the same, but they're going to be really close to each other at some particular pair of rounds. And that's when we reach agreement. So we're going to think about agreement in the same way that Scott Aronson did here. Okay. So we could try to just immediately apply this framework to our problem, right? We again have 2 agents. Okay, you know, one of them's a model and one of them's a human, but sure, we could say, okay, you know, what if they were fully Bayesian rational, right? Then we could, you know, instantiate an epsilon, and we could think about them going through an agreement protocol, where maybe the model says, okay, I think the risk of an operation is 0.2, and then the human, instead of just being sad because they disagree, they are going to update their posterior and send back there now what they think the risk of the operation is. And they can continue doing this. And if they really are Bayesians, indeed, it will be the case that with probability 1 minus delta over the draw of the prior, they reach a agreement within epsilon in 1 over epsilon squared delta many rounds. Okay, but this is maybe unsatisfying. And why is it unsatisfying? It's unsatisfying because this is a pretty intractable problem, right? The idea that the human is really going to be updating their posterior according to information, this is something that is quite complex. It's not necessarily an easy problem. And in general, even if it's something they could do easily, is it something that we actually think humans are doing? I think this is probably unlikely. And it's also, because it's so intractable, even though we maybe have some control over how the model acts, it's intractable to implement such a feature. Okay, and also all the previous results on agreement weren't known to generalize the multidimensional prediction. So we couldn't take that, even if we were okay with these really strong assumptions on Bayesian rationality, we can't necessarily take that and then, you know, like use it for the many realistic and common prediction studies we might care about, where instead of having a one-dimensional prediction, we're predicting a vector. So the main question in this paper is, can we relax this behavioral assumption of perfect Bayesian rationality while still maintaining good agreement convergence guarantees? And probably not surprisingly, because I'm giving this talk, the answer is yes. And we do it using tools from the calibration literature. Any questions before I continue? Okay, I will now provide an overview of the results. Okay, so conversation calibration is what we're going to call this property of predictions, which is going to be really helpful for us here. I will define it in detail and go over its definition soon. But it turns out that this is strictly more general than Bayesian rationality. So if you're okay with a Bayesian rational assumption, this satisfies that. But it's also weaker. There are things that aren't something that a perfect Bayesian would do that you can still get conversation calibration with. In fact, you don't need to have a shared prior, have a correct shared prior, any of that in order to achieve conversation calibration. And this is also something that we can now efficiently enforce on a model without accuracy loss in the limit. And okay, fine, but does it do anything good? The answer is yes. So if both agents have this property, then we now get back this fast agreement convergence condition in a repeated setting. I'll again talk about what I mean by repeated setting. And when these conversations go a little longer, this is going to always improve the accuracy of the final predictions. Okay, and finally, maybe you don't care about this repeated setting I'm going to talk about. And if you didn't care, we actually still have some results for you. Because we are in a because our conversation calibration condition is allows for a lot more flexibility, we're able to come up with results for multiple dimensions and for action feedback. And not only are these valid in the repeated setting, but we are actually able to, if the agents really are Bayesian, recover results in the one-shot setting using these new results. Okay. So moving on, just to get us all on the same playing field here, what is calibration? So imagine that you're a weather forecaster and you are trying to figure out the chance it will rain. And you say there's a 70% chance it will rain, and then it rains. I think it's a surprisingly tricky question of how to think about this, right? Did you do a good job? Well, okay, it looks pretty good. You said it was more likely than not to rain, and it did rain. But maybe you just got lucky, or maybe it was actually going to rain all the time, in which case 70% was low for no reason. So it's hard to tell in a one-shot moment, in the real world, whether or not your prediction is good. But what if I had a bunch more predictions? And I had a percentage every day of whether or not it was going to rain, and then we knew whether it rained or not. So now maybe we can do something, right? So now what might you want? Maybe I'd want to say, okay, now that I've seen days that you said it was going to rain 70% lots of times, I can check, did it really rain about 70% of the time on those days? And so we can see here, because I made it this way, that yes, that's true. But if you want to be calibrated, then we would hope that would be true for not just the 70%, but also the other times that you predict a certain thing, which we are going to think of as level sets. A level set is, all the times that you predict a certain prediction, right? So here we can see that on all the times that you predicted it would rain 20% of the time, actually it rained a lot more than 20% of the time on average. So you would say, this is maybe an indication that this weather predictor isn't very good. In particular, they are not calibrated. Okay, so this is just the formal definition of expected calibration error, which is one standard way of measuring okay, if you're not perfectly calibrated, then like how bad is it? Which is that you would look at all of your predictions, and you would kind of group them by, what type of prediction you made, right? Did you make it at 20%? Did you make it, 21%, 22, right? You have categories for each of them. And then on that subsequence of days that you predicted the same thing, I'm going to look at the total bias. And I'm then going to take the absolute value, because I don't want things to cancel out, right? When I predicted rain for that was, if I said 70%, but I was overestimating and I underestimated 20%, I want those both to be problems. I don't want them to cancel out. So I'm going to take the absolute value for each of these subsequences and then add it all up. Another way to think about this, right, is if you want to have expected calibration error of 0, which is perfect calibration, your predictions have to be completely unbiased with respect to the ground truth of subsequences that are defined by your own predictions. Any questions about expected calibration error? Okay, cool. So now we can get to our protocol. So before I discuss the idea of a patient coming in who had features which were something that could be understood by the human and understood by the model, here I'm going to formalize that by XTH and XTM. What is this T?
Natalie,
What's up?
can I ask a quick question about the calibration definition?
Absolutely.
The sum is taken over like a continuous interval, so the outer sum. So should I is there in practice, is there some like typical method for computing this quantity, or is it, can we think of it as an integral, or yeah?
So in practice, so when we think about a setting where you're actually just in a repeated game where you're making multiple different predictions, but for a finite time t, there's only going to be a finite number of different values that you ever predict. So it's not actually an issue, right? Like, so here we're kind of saying, it's not actually true that you're going to have an infinite number of these p's that
The
appear.
P is given as an input in this on the left-hand side. I see. Okay.
But it's also true that in general, the trick that you will do here is you're going to be often bucketing your prediction so that you even though it was already going to be finite, like you're going to try to reduce the number. If you have things that you would have predicted right next to each other, you're going to like clump them together. Does that answer your question?
Yes, thank you.
You're so welcome. Okay, great. So back to the sequential agreement protocol. Okay, so we can now imagine going back to this idea where they have this conversation back and forth. And maybe we've decided that, we're okay with 0.02 difference is our epsilon, and we will say they have agreement there. Okay. So, and then after that, say you maybe see the actual outcome. Now, what if instead of having this just happen once, this procedure happened many times, which doesn't seem totally unrealistic, right? Like, of course, the purpose of these sorts of medical decisions is you might have many different patients with different features, but who might have the same process to help them get help. So we can imagine having a transcript where we do this many times, right? And here we can think about this as basically being a table, right? Where from the left to the right, we're looking at days, right? Every day we have a new patient come in. And from up to down, we have the rounds of the conversation. So it's not going to be that every conversation is the same length. And every day, the patient can have different features. Okay, so I want to think about what conversation calibration is in this context. And I'm going to start by talking about perfect conversation calibration. Okay, so we're going to talk about this a lot. So no, don't worry if you don't immediately understand. I will have some visuals as well. But one way to think about this is that if I looked at the predictions that say the human makes in each round, right? So if we go back here and see like the risk 0.4, 0.11, this round, this can be like one particular set of predictions at that round too. Their prediction should be unbiased on the subsequence that's defined by the prediction of the other agent in the previous round and your prediction in this round. Another way to think about this is that in each round, your predictions are perfectly calibrated on subsequences defined by the prediction of the other agent in the previous round, right? Because calibration is basically the condition of just based on my actions, I'm unbiased. And so like we can either think about, encoding calibration as a condition here or not. Let's look at this visually. Okay, so if say that you have this is the transcript of play that happened. and I want to check, okay, is this perfectly conversation calibrated? So now I can look at any given round, and I can say, okay, let me look at the subsequences of my predictions at this round, given the bucketed predictions of the other person in the round before. So like, let's look at all the days that I predicted something in round 2. And in round 1, the other person or the model said something that was pretty close to 0.1. Okay, now on this subsequence, I would like it to be that I am perfectly calibrated. And what am I calibrated with respect to? With respect to these YTs, the ground truths that we see at the end of each conversation. So again, what we can think of here is when we define the subsequences by the actions that the other person took in the last round, here are the predictions, then we're looking for perfect calibration on these subsequences. Okay, and we want this to be true for in every round and for all the different subsequences defined this way. So this would be another example. Okay, so just to rephrase, right? Or not even rephrase, just to say it again. So these predictions are unbiased on subsequences defined by the prediction of the other agent, which we're going to bucket. Probably won't get too much into those technical details, but happy to answer questions about it if it's confusing. And my prediction this round, which I can also think of as just being perfectly calibrated on the subsequences defined by the prediction of the other agent in the previous round. Does anyone have questions about what perfect conversation calibration means? I've generally found that this is confusing for people, and I doubt I've done it so well this time that everyone understands it. So you'll be a hero if you have a question.
How come you're bucketing the other agents, but not yourself?
Sure. So why are we doing that? Well, the other agent has their predictions are we don't really have control, right, over what they do, right? They could predict like a different thing every single day. And it's going to be really hard for us to have any guarantees if we're thinking about the having to like have this guarantee basically be on like a point-wise day-by-day thing. On the other hand, we actually don't need to bucket our own because we're going to get this guarantee in a slightly different way where we will later alter this condition so that we do something which is a little bit like bucketing on our own. So if you think about it, in the final solution, we will end up with kind of bucketing on them and kind of bucketing on us, but defining it this way is kind of the cleanest way to see the result. Yeah. Okay. Right. So this is just written formally. Perfect conversation calibration. So, what is this? So here, this part is like the, the indicator variable that we are predicting a certain thing. And this is the indicator variable that in the previous round, the other person predicted something in a given bucket. Okay. So maybe you can see it's like a little similar to, conversation to just expected calibration error. And here we're not doing a absolute value because here what we're asking for is a for all condition. We're saying that like for all of these subsequences defined this way, the bias is 0. Okay, so why is this such a nice definition for our setting? So recall the thing that we wanted, which is that if both people were conversation calibrated, and here we're going to say they're perfectly conversation calibrated, even stronger, and we'll weaken that in a moment. Say they're perfectly conversation calibrated, then they should agree quickly. Okay, so why is that true? So here's a proof sketch for that. Let's consider some given round K, right? So this round is going to represent predictions on T different patients, or less if the conversation terminated before that round, right? But like every day is a different patient. But the thing that makes it consistent is it's like all of the different, this was always one person making this prediction, and it is always in the kth round. Okay, so and now let's think about the predictions of, say, the model in the next round, and we can think about how to compare them to each other. Okay, so there's 2 cases here. So the first case is that between round k of the human's predictions and round k plus 1 of the model's predictions, the agreement, which is when you get with an epsilon, this agreement happens at least half the time. Okay, so that's really good, right? So, because what we're trying to show is fast agreement. So if this case happened a lot, then we'd really quickly reach agreement. Okay, the second case is that's not true, right? You have not reached agreement in at least half of all rounds. Now, if that happens, what does that mean? Well, right, so what do we mean by you haven't reached agreement? Well, what that means is the predictions of the model in round k plus 1 on the days you don't reach agreement, each one of those days, it needs to be epsilon different from the prediction that you made at the round before, right? Now, why is this important? So there's a really nice key idea here that we're going to use. In general, the idea goes like this. Say that you have one sequence, which is calibrated, conditional on another sequence. So, all the days that you predicted X, I am unbiased. All the days that you predicted, the answer was Y, I am unbiased. Okay. So sequence 2 then has to have at least as low squared error as sequence 1. Okay. Why is that? Well, you can think about the fact that you can think about dividing the squared error by the subsequences of when sequence 1 predicts stuff, right? When sequence 1 predicts that the answer is 5, we are unbiased on those days. And so if they were already biased, then we're doing better. But if they weren't biased, we could still do better by just having a more complex sequence that actually gets it right more often, right? That's like kind of capturing the nuances in that average. Furthermore, we have to do this if we are doing something different than that, right? So if sequence 2 is substantially different than sequence 1, it has substantially lower squared error, right? So you can imagine a situation where sequence 1 is predicting, say that the actual state of nature is like 0, 1, 0, 1. Every day it switches. And sequence 1 predicts 0.5 all the time. So if sequence 2 is unbiased, conditional on sequence 1, right? If it's calibrated, then that means that sequence 1 is saying 0.5 all the time. Sequence 2, if it's doing something different, but it's still calibrated, it must be picking up on these 0, 1, 0, 1s, and thus actually be getting lower squared error. Okay, so this is like a nice trick that we're going to use. Okay, so to continue this proof sketch, what have we shown? So from round I to I plus 1, if we think about taking this transcript and kind of going down from round to round to round across all the days at once, either at least half of the rounds terminate from round I to I plus 1, right? This is agreement happens a lot, or the squared error goes down by a substantial amount. This amount, by the way, turns out to be epsilon squared delta. Okay, so that is how it works for perfect conversation calibration. And now we're going to add in one more thing, which is that would be great, but perfect conversation calibration is not possible in general. But approximate conversation calibration is. So I'm going to tell you what that is and why that doesn't mess up these results. Okay, so in general, the idea of sort of getting perfect unbiasedness according to any subsequences, that's really tough. So say you aren't perfectly conversation calibrated. What if you have low distance calibration on the subsequence defined by the predictions of the other person? Okay, what's distance calibration? This is a nice measure that's relatively newer, which is a different way of measuring how far you are from being perfectly calibrated. Instead of looking at expected calibration error, you can look at your sequence and you can look at the smallest, you can look at sort of all possible actual calibrated prediction sequences on this, things that are perfectly calibrated, and pick the one that has closest L1 distance to the thing that you actually did, and then look at that L1 distance. That's your distance of calibration. Okay. Does that make sense to people? So like, why is this a nice thing? Well, we'll see how it works here. So the way that we're going to define conversation calibration, right? Not perfect now, but with it's allowed to be imperfect, is that instead of being perfectly calibrated on conditions, on the sequences which are relative to the actions of the other agent in the round before, we're going to have low distance to calibration on these subsequences. So we are now parameterized by the bucketing of the other person's predictions and our distance to calibration F. Right, that's here. This is the distance calibration, this is the bucketing. So why is this enough? So remember what I was saying before that, okay, you would either agree a lot of the time or your squared error would decrease substantially. So we don't actually have perfect calibration error, but we have low distance to calibration. So what we're actually getting in terms of squared error can't be that different than that result that we got for the perfectly calibrated predictor, right? And this is this really nice property of distance to calibration, which is that it's Lipschitz. And when you are measuring things that are Lipschitz, using distance to calibration is just as good as ECE. Why would we use this then instead of ECE? Well, it's just as good in that it gets the guarantees we want, but it's actually better because we know of how to get something that goes in root T for distance to calibration, while we know that's not possible for ECE. So we're going to take advantage of the fact that in this case, we don't really need to get low ECE. Getting low distance of calibration is enough. Okay, so going back to our proof sketch, because we still have to put the pieces together. Okay, so now what we have is, remember, perfect conversation calibration said that when you analyze round I to I+1, you either have a lot of agreement or squared error is going to go down substantially. And it turns out that while we can't actually get perfect conversation calibration, we can actually get approximate conversation calibration. And this property still holds true for approximate conversation calibration, where of course we're going to have this epsilon squared delta be weakened a little, but the term that it's weakened by is going to be sublinear. Putting this all together, right, like roughly we can say, okay, what's the total number of rounds that we can disagree, right? So it's roughly the max possible squared error you can start with, divided by the decrease in squared error whenever less than half of all days terminate. Now here, notice I've sort of just excluded all of the rounds where we're agreeing at least half the time. That's both because these rounds are tiny, right? It's like a log, but also because in the actual analysis of the paper, we don't use this trick. That's more of an explanatory part. We're actually just able to have the bounds be directly in terms of this ratio. Okay, right. So if we think about, having like a normalized thing, your max possible squared error is 1. And the decrease is, as I said before, epsilon squared delta minus sublinear thing. Okay, this leads us to our main theorem, or one of our main theorems, which says that if the human is conversation calibrated and the model is also conversation calibrated, then for any epsilon and delta, you're able to reach epsilon agreement after most k rounds of conversation. And where this k looks a lot like the 1 over epsilon squared delta that was in the Aronson agreement theorem, where we just have this sublinear little beta here. And furthermore, it would be nice, right, if not only are we reaching agreement, but because we have this squared error potential-like argument, we can say something also about the fact that we actually are improving in squared error whenever we don't agree, right? So if you do make it to round I, then you've gotten there because the squared error that you have has decreased from the start by something that also scales with epsilon squared delta. Any questions about this? Okay. So just in case you are curious about what this beta term looks like, I'm going to flash it up here, right? And you can see that it includes, like for both the model and the human, it includes their distance of calibration term, and it includes their bucketing term of the other person's predictions. But there's ways to set all of these 4 values so that what you end up with here is something that is sublinear in T.
By
fact,
sublinear, I assume you mean going to 0.
Yes, yeah. In fact, not sublinear in T, but yeah, like something that as T gets large goes to 0. Okay, cool. So just showing this here because we ended up being able to use this algorithm for what we're doing, right? I was talking about how we were using distance of calibration because we actually have an algorithm that gets root T distance of calibration in the adversarial setting. I don't expect you to read this, but I just want to show you that it's very short, it's very simple, it's actually deterministic. And so this is pretty nice. Okay. So when you use that particular algorithm and the guarantees it get, in the distance, okay, so just back up for a second, right? So okay, so this is nice, but we need to talk about how to actually guarantee that both the human and the model in fact get a reasonable F and G, right? I told you, oh, we can pick them, right? But maybe we can't necessarily pick them. We have to come up with algorithms that generate them, right? And in particular, like maybe we can assume for a moment that the human is, maybe they are able to do this, maybe they're Bayesian, or maybe they're able to do at least as well as they would by some like adversarial thing that we can ascribe to the model. So let's worry about the model and sort of force them to get this, right? So the model can use an algorithm which augments itself with this square root T distance of calibration algorithm. And then when the G and the H that we pick give us that this beta T is T to the negative 1/3. So this is pretty good, right? Okay. And the way that you would do that, again, don't expect you to read this, is that the model could start by just honestly predicting its original base model predictions. And then every round after that, on the subsequences defined by the predictions of the other person, it would run this is a calibration algorithm directly. Okay, so that's nice for the model. And then for the human, as a reminder, conversation calibration, this thing we've defined, is satisfied by Bayesian updaters. So if there really was a state of nature, a prior over the state of nature, and they really did update their posterior according to this, then they really would have conversation calibration. So what this means is that if you were happy with the agreement protocol before, now we're able to just say sort of like a strictly more general thing, because it's not just true there, right? You don't actually have to know the state of nature. As we've seen here, you could get conversation calibration in an adversarial setting. Okay, but maybe you really do care about the one-shot setting, and you really care about Bayesians, and you don't care about adversarial notions. You really think that people have a good sense of the world. Now, if you think that, we still have something interesting to tell you, which is if the human and the model are, oh, sorry, I think I have this out of order. Cool. Right. Okay. So what do we have to say? So remember that conversation calibration is a condition that holds for any T, and that we have this beta T that gets to 0 as T gets large, right? So what have I done here with like all these different rounds? Well, imagine that you have just decided to run this for T is a huge number, something approaching infinity, just a really, really big T. If you make T bigger and bigger, it's just going to force this beta as small and small as possible, right? So if we do that, then what we get is that for that particular instance, this beta basically goes away, right? And essentially we get 1/epsilon squared delta is the number of rounds that we can reach epsilon delta agreement in on this sort of imagined scenario. Okay, why am I doing this? So now in this huge, very long interaction time, let's think about what's really happening. Because I'm saying, let's assume that the human and the model, instead of being a human and a model, are actual Bayesian agents. Now, what does that mean? That means that every day what's really happening is there's a shared prior and it's independent every day, and they both get hidden information every day, and they are having a conversation that is completely unrelated to the previous days, right? You can get conversation calibration without doing this, right? But you really have to use previous days in order to do it. But if you really are Bayesian, you don't have to do that. And in fact, definitionally, you will not. You will have a conversation that is completely independent of the previous days. So what that means is that these days are permutation invariant. So I could take the results of the conversations and I could randomly permute them. And this would, all of these conversations on those different days would still be consistent, right? So maybe another way to think about that is if I define this transcript of play by the shared prior and then the hidden piece of information that happened on every day, if I permuted those and reran this whole thing, then wherever I had moved that shared prior and the hidden information would generate the same conversation wherever it is in the transcript. Now, why is this important? This is important because now, like, what was the guarantee we got from this theorem that we had? The guarantee was that on a 1 minus delta fraction of days, we're reaching epsilon agreement in 1 over epsilon squared delta many conversations. Now that we permuted the days, what that means is that there's a 1 minus delta chance that the short agreement is reached on the very first day. And so we don't really need this repeated notion at all to be able to make a guarantee and say that with 1 minus delta probability over the draw of the prior, we are reaching epsilon agreement, and at most 1 over epsilon squared delta rounds. Okay, so what's notable about this? Well, this is interesting because what we're saying is, even though our definitions and many results are in this repeated setting, we are able to directly recover the Scott-Aronson results in the one-shot setting. And furthermore, I don't know if I'll have time for this, but we're able to strengthen those results because we are able to reason about multidimensional prediction as well, and then use this idea to construct results in the one-shot setting with actual Bayesian learners. Okay, so why is any of this interesting, right? Why do we care? Well, it really does seem like this is something that people are thinking about now, right? Thinking about AI, thinking about how it can be used in medical contexts, other contexts with professionals. But I think there's a lot still left on the table here to think about, right? I think a lot of early studies have suggested that, in fact, we aren't successfully finding ways for humans and AI to collaborate with each other in a way that augments the final results. And so maybe coming up with more formalizations, ways to think deeply about this could help. Right. Yeah, that. And so a couple sort of follow-up things one could think about here is when thinking about how to ground this in the real world, you know, are these behavioral assumptions that we came up with, are they actually sufficiently weak? We need to weaken them more. And can we use insights from the theory we have here to actually design better human AI protocols other than the ones that are using these experiments now, which I assume aren't, deeply grounded in theory. Okay, so going back to the overview of results, conversation calibration is this notion I've introduced to you, which is strictly more general than Bayesian rationality and is efficiently enforceable on some model. And this will, in this repeated setting I've discussed, imply fast agreement convergence and conversation accuracy improvements when the conversations go longer. And if the two agents really are Bayesian, then we are able to recover Scott-Aronson's 2004 results in the one-shot setting and generalize them to multiple dimensions and action feedback. Yeah, I have I could keep going. I think I have some extra slides here, but given that's 12:50, I don't know how much time we generally leave for questions. I will stop for now.
You could take 5 more minutes if you wanted, and leave 5 minutes for questions, but it's up to you.
Tell us what
Yeah.
action feedback is.
Okay. Let's see if I have it here. Maybe I don't have the slides here, but I can talk about it. Okay. Yeah, maybe I overpromised an action feedback, but let's see. Okay. What's action feedback? Okay. What's action feedback? Action feedback is instead of having the prediction be just what is Y, you could imagine instead Y being some complex multidimensional thing, right? And the prediction is on what is the best thing to do given Y, right? So you can imagine a situation where Y, this prediction, is on a bunch of different, health information about this patient, right? Generally like tons of different risk scores they could have. And the thing you're trying to predict is just, should we do the procedure or not? Right? Now, this is a nice model, which I think, like in general, Aaron has done a lot of really cool work in thinking about how action feedback can be used to make calibration protocols more efficient, because maybe you just need to calibrate on the thing you actually care about. And in this context, what it means is maybe we don't actually need to be calibrated on a particular, like sort of like the entire space of some complex multidimensional vector. Maybe we can just be calibrated on the thing that you want to predict. And what we're able to show is that we can get guarantees which are going to be independent of the dimension of the actual vector, but where you are able to agree that something that scales very similarly to what's going on here when we're agreeing with action feedback. We also have results for multidimensional where you're actually directly making predictions on the multiple dimensions. And in that case, we have something that does scale with D, but D is pretty good, we think. Yeah, so that's, yeah, that's that. Any other questions?
Left everyone speechless.
Is anyone, if you have a question, which is what is conversation calibration, I still don't get it, that's a fine thing to ask. I would just be surprised. Like, I've never given this talk and had 100% of the time someone has been confused at the end. So, but that's okay. Maybe I just did too good of a job.
You've done an excellent job.
I agree.
Let me ask kind of about extensions.
Yeah.
So people don't necessarily understand probabilities, right? That's kind of even input from other, like if they don't know how to interpret a model telling them 60% or 70% and are not calibrated in so is there a thought of getting inputs in other ways that are perhaps not exactly
Yeah.
probabilities or like
No, that's a
agreeing
great question.
on kind of big things like high risk, slow risk, or agreeing on an action or agreeing on something
Yes.
easier to kind of
So we actually, sorry, I didn't mean to interrupt. Okay, yeah, that's a great question. And yes, it's something we've thought about, and I agree it's a good extension. So, actually in the original Aronson paper, one of the things he's doing is not just showing that the number of rounds is small, but that the communication complexity is small, because in his paper he shows a way where instead of communicating the actual expectation, they're able to communicate like, oh, it's lower than I thought. Like, I'm lower than you, I'm higher than you, right? So they can just do a low high or agree. And I think it would be very reasonable to extend that to our setting. So where if instead of the human having to communicate, okay, this is exactly what I think a probability is. They could communicate, okay, well, you say the probability is 50%. I just have a sense it's much lower than that. This is something that we talked about. In the end, we didn't end up including it. It was like, frankly, I think it was just because it was harder for me to prove than I thought it would be, but I think it's possible to prove. But I guess even in that case, it seems like one of them, the human would need to either understand or communicate probabilities.
And maybe just to like say a little bit about the action feedback setting, which I think is similar in spirit to what you're suggesting. Right. So like the label space could be 1,000-dimensional. Maybe there's 1,000 diagnostic codes at this hospital, and so like what we're arguing about is what is the distribution over the whole sequence of diagnostic codes. But like we don't want to engage a doctor in conversation that obligates him to like speak out 1,000-dimensional real valued vectors every day. And so the action feedback setting says, look, there's some set of treatments that the doctor has available to them, or diagnostic tests they can, some set of things they can do. And there's a utility function that maps the thing you do and what the actual realized disease was to some utility. And the conversation can take place in the space of best response actions. We never need to talk about numbers. We can say, you can say, I think we should amputate the left arm. And I can say, I disagree. I think we should amputate the right arm. And we can go back and forth in that space and eventually agree, even more quickly, in fact, on the best response action. But it does mean that, like, but what is the assumption that goes into this? The assumption that goes into this is, even though we're speaking about actions, like, and the reason we're speaking about actions is like, implicitly because we think, you're not able to like enunciate these like, complicated probability vectors. The assumption is still, though, that somehow, like, unbeknownst to you, implicitly, when you speak your action, it is a best response according to some vector that satisfies conversation decision calibration. And so like the assumption is still sort of hidden in there somewhere, but at least we don't need you to explicitly speak in the language of probabilities. The other thing you could say is that, like, just as you can take an arbitrary model and cause it to be conversation calibrated while only improving the accuracy, you can do the same thing to a person, right? Like if you have this doctor who is trying to vocalize probabilities, but like they're just really badly calibrated, you could hand them a calibration megaphone and they speak into one side of the megaphone and other probabilities come out of the other side. And you could design the megaphone so that the things that come out are conversation calibrated and are only more accurate in terms of squared error than what was spoken in. So you could aid the doctor in that way as well.
So the model will then get to the right conclusion, right? But the human, would the human agree?
That's right. So now agreement would be like agreement with the megaphone, which is
right.
Not quite the same thing. Yeah.
I've seen a kind of empiric study that talked about essentially manipulating the humans. So giving them the kind of information that they need. So I'm making a recommendation instead of saying 60% or 70%, which they don't understand. I'll tell them 80 or 90 to convince.
I've seen these. I'm sort of skeptical of this kind of thing because I think what they're getting at is some like static phenomena before the human being catches on. Like I think if your plan is to like lie to the human to manipulate them, like eventually they're going to change their decision rule to like once they figure out what you're doing.
Yeah, I had a very similar reaction, and I thought that eventually the point is not to lie. The point is to have input in that human can relate to, and they can't relate to 60% or 70%, but they can perhaps relate to high, I don't know, high priority, low priority, I don't know.
Yeah. And I guess to the extent that So you could coarsen the probabilities to, you know, high, medium, low, to the extent that they're making their decisions with respect to these coarsened probabilities. Like that, if they internally are representing their utility function in terms of these coarsened probabilities, then everything should go through. Like, you know, you can talk about calibration with respect to this coarser metric. But like the bigger problem would be if like the way people are behaving is actually like inconsistent with the, you know, any probabilistic understanding of the world at all, which might be.
Cool. Well, thank you so much for all of your time. If anyone has, other thoughts or questions about it, those of us who have worked on it are considering follow-ups. We think it's a fun space, so feel free to shoot us an email or chat with us about it. Thank you all, and have a great day.
Thank you.
Well, thanks a lot, Natalie, for the great talk. And yeah, we'll definitely chat soon.
See you later, alligators.
See you.